Hi, I'm Jemason. Today we are going to look at integration by substitution, and in particular we'll be focusing on the shortcuts that are involved whenever you are dealing with integration by substitution. Shortcuts are particularly used especially where substitution is obvious in the question. There are questions where there is substitution in the integral but the examiner doesn't tell you. There are others that will say evaluate this integral using this substitution. Where it is not obvious, the examiner suggests the substitution that you're going to use. Majority of the cases, they don't suggest, so you are the one to decipher that I'm going to do substitution in this integral. Now the question is, how do you quickly recognize that there is substitution in this particular integral? That is the first thing we want to see. Generally, if you see an integral and the function that you are supposed to integrate is such that part of the function can be differentiated to have the other. You can see here, this integral involving e to the f of x, the power of e can be differentiated to get this other function that is multiplied by e to the f of x. In this other case, we have cos f of x, and f of x is differentiated to have the function that is multiplying cos f of x. So there is part of the function that can be differentiated to get the other part. Again, when you notice that, know that there will be substitution. How do you now do the substitution? You let u to be the part that can be differentiated to get the other part. So in this integral, I would have said let u be this power of e. Let u be f of x. And then I will do my substitution. In this other one, I will say let u be f of x, and then I will do my substitution. Usually it is quite lengthy, and so there is the need for us to see how some shortcuts can help us to get our integral in a few steps. The principle behind the shortcuts is actually the fact that differentiation and integration are opposite processes. If you observe here, you will discover that if I differentiate e to the f of x, I get f prime of x e to the f of x. And so it is but natural that if I integrate that function, I should go back to e to the f of x. That is where the shortcut is coming from. When you have noticed that this shortcut, what has happened? They have simply ignored the f prime of x and then written the answer simply as e to the f of x. In the course of substitution, f prime of x would disappear as you are trying to replace the dx, which is in terms of x, by du. That is where the f prime of x will disappear, and at the end you will just have something like e to the u to integrate with respect to u, and that simply gives you e to the u plus c, and u is f of x. That is where all that process usually happens before f prime of x would disappear. So when you arrive there, notice that there is f prime of x multiplied by e to the f of x. Just ignore f prime of x and then copy e to the f of x as the answer, plus the constant of integration. Let us see an example. If I have integral of cos x e to the sine x dx. As you can notice, e to the sine x, the power of e can be differentiated to have this part, which is cos x. And so in that case, I do not need again to do a lot of substitutions and wasting time in the exam. I simply go straight because the method is clear. I notice that there is a function that if I differentiate, I will get this part, and that function is e to the sine x. So I simply ignore the cos x and then write the answer as e to the sine x plus my constant of integration. Most of the cases will not be as easy as this one, where the differential is just beside the function. Take this other case, integral of x squared e to the x cubed plus 1 dx. In this one, we notice that if we differentiate the power of e, we have 3x squared. But what we have here is x squared, and so it can be modified to have the differential so that f prime of x would be in this position here. And the simple thing I can do is simply inserting a 3 here and then neutralizing it with 1/3. When I do that, I will now have the exact differential of the power as the product or the other factor with which e to the f of x is multiplied. So I will have 1/3 integral of 3x squared e to the x cubed plus 1 dx. Now this setup looks exactly like the shortcut. There is e to a function and the differential of that function is beside multiplying the e. So it implies that I will simply ignore the differential and then copy e to the x cubed plus 1 as the answer. 1/3 remains outside as that constant that neutralized the 3 that I inserted there, and it changed my function. So I have to neutralize it so that the original function does not change as I'm doing the integral. So I will now get e to the x cubed plus 1 and then plus the constant of integration. And that is your answer directly. If you had to do substitution, you would have a lot of steps to do, especially when there are even limits. You would need to convert the limits to reflect the new variable, and all that takes a lot of time. So where there are shortcuts, you are permitted to use them so that you move faster. Maybe you would want to try this one, integral of, let us say, sec squared 4x plus 3 e to the tan 4x plus 3, all that dx. You can try this and see whether you would get the answer. Okay, moving over to this other situation, we see that if I take an example now, for instance, I have integral from 0 to the root of pi on 2 of x sine x squared dx. That is a past exam question, GCE. Now, when I come here, first of all, let me go back and explain what happened there. So here, once you notice that there is a trigonometric function which has a function f of x, and there is the differential of that function that is multiplying the trigonometric function, simply ignore f prime of x and then change the trigonometric function to the corresponding integral. Remember, when you integrate cos u, for example, you would have sine u. That is where this one is coming from. So normally any trig function that is here, whatever, it could be tan, that will be there, it could be whatever trig function, it could be sine, like in this case. You simply ignore the differential that is multiplying the trig function, then change the trig function that is there to the corresponding trig function that you usually obtain when you integrate that trig function that is there. So we notice that each time you integrate cos x, for example, you have sine x. So if I integrate cos u, because that f of x was supposed to be my u, I will get sine u plus that constant of integration. So what happens here now, again, is that if I differentiate my f of x that is there, which is x squared, I get 2x, but I have only x here, so 2 is not there. So I would again in one step modify my integral and then be able to write down the answer. So there is a 2 that is lacking here. I'll put 2 and then neutralize outside with a half so that it doesn't change my integral. That gives integral from 0 to the root of pi on 2 of 2x. I've inserted a 2 and it was not supposed to be there, so I neutralize outside with half, just like I did here, inserting 3 and neutralizing outside with 1/3. So here now I will get sine x squared, all that dx. And so from there now, the shortcut now tells me I have to ignore the differential and then change the trig function that is there into the corresponding integral of that very function, that very trig function, maintaining my f of x. So this gives half into, I ignore the differential, then change sign to the corresponding trig function that is usually given when I integrate sine u or sine x simply. So this gives me negative cos x squared, and then from 0 to the root of pi on 2. And since there are limits of integration, I would now proceed to do my substitutions. I get negative half cos of root of pi on 2 all squared minus minus half cos of the root, cos of 0 all that squared. That gives me negative half cos pi on 2 plus half cos 0. And here, cos pi on 2 is cos 90, which is 0. So this gives me 0 plus half. And then cos 0 is 1. And so my answer is half. So that is the way this other one operates. Okay, maybe you can try this one. Integral of x squared sec squared x cubed dx.